Hey everyone, Joey here. I'm going to bring you through a quick PowerPoint presentation that I would normally have split up over the last few weeks before labs to get you ready for the lab activity. But since we're doing this remotely, I'm doing it now as sort of a recap to all the information, the kind of super heady information that we did earlier this week. So here we go, let's go. So when we're identifying minerals, your mineral identification toolkit, those lists of physical properties, that's exactly what you're going to use to identify minerals. My thought process when I go through it, first thing I think is the luster. Is it metallic? Is it non-metallic? The hardness, I test it with a fingernail, with a penny, with a knife blade, against quartz and then topaz, and that gives you the range of hardness. I look for the streak color. I see if I can find any cleavage faces glinting at me to give me an idea of how this mineral is breaking. If it's a clean cleavage face, that gives you a better idea of it. It narrows down what you're looking at. Specific gravity. How heavy does it feel? For instance, topaz and quartz, they can both look very similar, but topaz has a much higher specific gravity, and you can feel that in a hand sample. Special properties. Does it fizz? Is it magnetic? Does it double refract like calcite? All of these things help you narrow down what you're looking at. The lab book, what normally you would use your lab book in the lab, going through and looking at the physical properties listed, we've recreated the lab book. So the weekly lab modules are your lab book. All the information is there, all the physical diagnostic criteria. You just need to look at that and narrow down what mineral we're trying to get you to identify. Here's a little flow chart that you can work through. It's basically the same as what was on the last slide, just in a different format. You can start luster, non-metallic. Is it dark? Is it metallic? Is it magnetic? There's only one mineral that we'll ask you about that's magnetic. That's magnetite. If it's non-magnetic and has a metallic luster, is it silver? It's scalena. If it's gold, it's either pyrite or chalcopyrite. If it has visible crystals, it has that cubic crystal form, then you're looking at pyrite. If it doesn't, you're looking at chalcopyrite. So that's how you use this sort of flow chart. Feel free to pause the video, look at this. I think we could also get you a copy of this if you'd like. We can put it in the class files or something. So silicates versus non-silicates. Silicates have the silicon tetrahedron. Non-silicates do not. We went over the native elements. These are singular elements. Gold, copper. They're not compounds like galena, which is lead sulfide, PbS. These are individual elemental minerals. The sulfides here, these are the four that we'll be asking you about. We won't be asking about bornite, arsenobornite, arsenopyrite, or stibnite, or molybdenite. It's just these four right here: galena, chalcopyrite, sphalerite, pyrite. Galena is lead. It's heavy. It's dense, gray, gray streak. Pyrite also has a gray streak, but it has those gold cubes that it forms. Chalcopyrite is more massive, and sphalerite, blackjack, it has a yellow streak. The sulfates, very soft. You can scratch them with your finger. 3 varieties of gypsum we'll be asking about: alabaster, selenite, and satin spar. Satin spar is very fibrous. Selenite is like window glass. And alabaster has that sort of rock sugar texture to it. They're all very soft. You can scratch them with your fingernail. The oxides are metals mixed with oxygen. The 2 that we will have is hematite and magnetite. Magnetite is generally magnetic. They're both metallic luster. Hematite can be silver, it can be red, but it will always have a red streak. So it can also be metallic, or it can be magnetic sometimes. So if you're looking at 2 pieces of a dark colored rock, both magnetic and the streak is red, you know you're looking at hematite, not magnetite. Magnetite has a dull gray or black streak. The halides, they're halite and fluorite. They're a metal cation mixed with a halogen anion. Here's fluorite here. Here's halite. You can see they have this nice cubic crystal form. Halite actually cleaves cubically. Fluorite cleaves into octahedrons, which is like a double-sided pyramid. Halite is relatively soft, as is fluorite. Fluorite has a hardness of 4, so we'll scratch a penny. You can't scratch it with your fingernail because your fingernail's around 2. Will not scratch glass, either of these. Halite has a real greasy feel to it, and it tastes salty because it's table salt. Carbonates. One of the special properties of carbonates is because of this carbonate radical here on the end, the CO3, when we drop acid on it, we release the CO2. It's the same stuff that makes sodas fizzy. So these minerals, if we drop a little acid on it, they will effervesce or fizz. The ones that you'll be asked to identify are calcite and dolomite. The one thing about dolomite is it has this magnesium locked into the framework, or the molecule. So that makes it a little bit denser, makes it a little bit tighter, so it will not often fizz directly. So you have to shave off a little bit with a knife and get a little powder. And then when you have that powder and you drop acid on it, then you'll see the effervescence. Phosphates, the one we'll be looking at is apatite. They have the phosphate anion. Has a hardness of 5. It's one of the tougher ones to identify, but if you pin the hardness down, if it's between fluorite and apatite, or between fluorite and a feldspar, or fluorite and quartz, you've got a pretty good idea that you're looking at apatite here. So let's move on to the silicates. As we talked about, 90% of the crustal minerals are silicates. The main component of silicates, the building blocks of silicates, is the silicon tetrahedron with a silicon ion surrounded by 4 oxygen ions in the anions in these this little pyramid shape here. There's different arrangements that divide them into the silica tetrahedra, the different framework structures. So as you can see here, we've got the isolated, the single island, lonely tetrahedron. Olivine is the example of that. We've got single chain and double chain. The single chain is the pyroxene group. The double chain is the amphibole group. These are both inosilicates, INO. We've got sheet silicates, which make up the mica and the clay groups, and that's a bunch of sheets on top of each other with cations in between. The silicon tetrahedron is the strongest bond. It's a covalent bond. They're ionically bonded to metal cations in between, and those ionic bonds are much weaker than the covalent bonds. So when those break apart, that's where they're going to break, and that's why they break into sheets. And then we also have the tectosilicates, which is this framework silicate structure, quartz, feldspar. It's a 3D framework where all these silica tetrahedron are all sharing. The ratio is 1 silicon to 2 oxygen, since all of them are being shared. Not shown here are cyclo and sorosilicates. Cyclosilicates are rings. They form ring chains of silica tetrahedra, and the sorosilicate is like this isolated silicate structure here, except for there's 2 of them. So there's 2 pyramids. It's like a bow tie shape. Again, here's another infographic about the various structures. And yet another one to make it even more clear. One thing you can notice here is that these ones on the top, olivine, pyroxene, amphibole, biotite, they all have iron and magnesium. These are ferromagnesian silicates. These tend to be darker, olivine dark green, pyroxene, amphibole group black, dark green, biotite black. They are darker. They're a little heavier than the non-ferromagnesian silicates. These have lighter colors to them: calcium, potassium, aluminum, sodium, calcium, as you can see down here. And you've been seeing this a lot in your lab book last week. This just shows you the connection points with the oxygens of all the different frameworks. And as I was just discussing, there's two main families of silicates, the ferromagnesium and the non-ferromagnesian. Ferro is iron, magnesium is magnesium, so the non is without. But here's sort of what I was just saying on the last page. We've got a hornblende here, augite, olivine. For the ferromagnesian ones, they're darker color, dark black, dark green, gray. They crystallize out of melts at higher temperature. We'll get into more of that next week with Bowen's reaction series and igneous activity. They contain more iron and magnesium and less silicon. The non-ferromagnesians, we've got orthoclase, albite, and oligoclase. They tend to be lighter in color, pink, white, light gray. They crystallize out at a lower temp. And as I said before, they contain more potassium, sodium, and calcium. Quartz is our first tectosilicate. It's everywhere, as you can imagine, with quartz and silicon making up the majority of the crustal materials. It's the primary ingredient in beach sand. We see it everywhere. Quartz has these nice hexagonal crystals. You can see it comes in a variety of flavors based on small little bits of impurities that get in there. This is smoky quartz. This is rutilated quartz. It actually has rutile minerals growing through it. This is your standard quartz. Everyone's seen those crystals. And here's rose quartz. The feldspar group is also tectosilicates. You've seen this image before. Right here we have the alkali feldspars, or K-spars, and then here we have the plagioclase solid solution series, going from the sodic-rich sodium albite all the way to the calcic-rich, calcium-rich anorthite. Orthoclase will be the one that's in your, we'll be testing you on. It's potassium feldspar. It's the most common variety. You'll notice this by the right angle cleavage and the perthitic structures. That's sort of this this veining that's on there. It has to do with the cooling history, and there's two slightly different mineral varieties in there based on the flux melting within the magma chamber, which is a little bit above what we'll go into for this class. But just so you know, that's where the perthite or the perthitic structure comes from. Next is the feldspar, the plagioclase solid solution. As we said, the sodic-rich goes all the way to the mafic-rich. Depending on the cooling history, there's different percentages, and percentage of sodium to calcium, and this is the spectrum. Goes from albite all the way to anorthite based on how much sodium and calcium is in it. The non-ferromagnesians are felsic. The ferromagnesians tend to be mafic. And it's kind of the same here. Calcium is more associated with the mafic side of the spectrum, and sodium is associated with the felsic side of the spectrum. This also has 90-degree cleavage because it's still a tectosilicate arranged in a similar way as the K-spars in the last slide. But these will always show striations, perfectly parallel lines or grooves, which you saw in an image last week. But on the cleavage plane, you'll always see those grooves. It's a good indicator. If you see those striations on a piece that's breaking roughly 90 degrees, you know you're looking at a piece of plagioclase. Pyroxene group, this is augite, single-chained Innosilicate, generally dark green to black, near 90-degree cleavage. It will scratch glass. It's common in igneous rocks. The way you can tell this apart from hornblende is that 90-degree cleavage. Hornblende is an amphibole, also an innosilicate, but a double chained. And this breaks in that 120-60, so those acute and those obtuse angles. You can kind of see it here. If you look, this is sort of an acute angle, this is an acute angle, and then opposite that is an obtuse angle. You'll generally see those the way that they break. You know, if you're looking under the microscope in an igneous rock, you'll either see squares or you'll see sort of you'll see those oblong or those obtuse angles in there, or this fibrous habit, and that'll tell you that you're looking at an amphibole rather than a pyroxene. And then we have, moving on to the nesosilicates, the island silicates. We've got this is basalt rock, and this is that olivine that's attached to it. This is what we would call like an aggregate, a granular aggregate of olivine. Olivine does not cleave. It's always this kind of greenish to dark greenish color. These little black bits in here are pyroxene, probably augite or something like that. Garnets, they're a little complicated, but again, nesosilicate, they do not cleave well. They fracture. They're often distinguished because of these dodecahedral. You'll see this shape with these little soccer balls all over the place. You'll see that often, or you'll see this sort of this very geometric look to it. The way you can distinguish these is garnets are hard. They will scratch quartz. They have a hardness of 6.5 to 7.5. Will often scratch quartz. If you have a 6.5 hardness and a 7 hardness quartz, it won't scratch, but generally speaking, they will scratch quartz. Topaz, as I was saying earlier, it can often be confused with quartz, but it has a much higher specific gravity. If you have two pieces that are roughly the same size, the topaz will be much, much heavier. It's also harder. It's the Mohs hardness scale mineral at 8, so it will scratch quartz. There's not much. There's practically nothing in your boxes that won't be scratched by topaz. Obviously, we don't have diamonds, and we're not going to have corundum either. Corundum is 9, diamonds are 10, just because they're too valuable. But basically, nothing else will scratch topaz in your specimen. Okay, moving along. Next up, we have the phyllosilicates, muscovite, biotite, phlogopite, lepidolite. The only two you'll be quizzed on are biotite and muscovite, black mica and white mica. They're sheet silicates, as I was explaining earlier. They break off into sheets, real neat basal cleavage. They tend to be flexible. They won't break when you put some stress on them. Talc is very soft, has a hardness of 1. You'll be able to scratch it. It has a greasy feel, and that's the sheets of talc coming off on your fingers when you're rubbing it together. You can see here it has that greasy look to it. Here and here, it can be a variety of colors, but generally it's sort of this white, greasy, resinous kind of look to it. Chlorite is a little harder than talc. Most often you can scratch it with your fingernail. Sometimes if it's on the little harder side, you can't quite do it, but it will scratch nicely across a streak plate, and it'll have a green streak. It's common in metamorphic rocks and green schist facies rocks. It can be a variety of colors. Most often though, it's sort of this greenish, speckled greenish black look to it, and you can feel it with your nails. You can feel that you can almost scratch it which lets you know that it's fairly soft. Kaolinite, hydrous aluminum silicate. This is a weathering product of the feldspar group. These are clay minerals. You'll see them in soils. You'll see them all over the place. It kind of feels like chalk, except for chalk is calcium carbonate. We'll get into that in sedimentary rocks, but as you can see here, it's white. It'll streak off. It'll powder on your hands, and you can see that white powder. Yeah, it's very similar to chalk, but chalk is calcium carbonate, and this is a silicate. I want to bring your attention again. A lot of the images and sort of links I've been putting in the modules so far, a lot of them come from MinDat, minerals.net, and geology.com, mineralseducationcoalition.org. These are all great resources if you want to do a little deeper dive or spend some time getting to know the various minerals that we're dealing with, and also just cool other minerals that we don't have the opportunity to look at. But yeah, I would like to highlight these again just to keep in mind. There are a lot of resources out there, and it's only going to help you. The more you look at stuff, the more it helps you. There's an old saying, the best geologist is the one who's looked at the most rocks, and that holds true. It's the more time you spend, the more you can revisit the information, the better it sticks in your brain. And that's all we have for this. So I will stop right here, and good luck next week.